This lesson deals with a Pspice simulation of a common-emitter amplifier. You can find these notes in the ECE302 ebook in Chapter 5, starting on page 8. I took our schematic of the common-emitter amplifier and I numbered all the nodes. You can do this in any order, but the ground node must be labeled as 0. I'll explain these graphs after we finish the simulation. My Pspice file must have a title, and then I describe the schematic. My battery is between nodes 4 and 0, and it's 15 volts. And then I have resistors that are between two nodes and have a value. There are capacitors between two nodes and have a value. The first node you pick is considered the plus terminal, and the second the minus terminal. So if you ask for a current, it's going to flow from the first to the second. Same will be true for the capacitors that are here. My AC voltage source is from nodes 1 to ground. If you recall from 202, that's how we described an AC signal. And then the value is 1 millivolt. M in Spice, whether it's uppercase or lowercase, refers to milli. If you have meg, it's just MEG. The next line is modeling the transistor, so dot model. Our textbook called this QMod, so I'll just call it the same. And then this is an NPN transistor. I'm going to use the default values. I'm going to do a Bode plot with the dot AC from 1 hertz to 10 kilohertz. I'm going to do 50 points per decade. That's going to give me 200 data points. I'm going to ask for the operating point. And then Pspice has a feature called dot probe, which allows you to look at any voltage or any current. And our last line must be a dot end. Ran the simulation. I printed out here the operating point information. So it gave me the DC results here. Base current, the collector current, the base emitter voltage, the base collector voltage, and the collector emitter voltage. And then calculated the DC beta, found R pi, and found the AC beta. We'll later see that these two are not going to necessarily be the same. From this operating point information, we see that the base emitter voltage is not 0.7, which is what we assumed when we did the hand calculations previously. It's actually 0.81. If I want to compare these results to my hand calculations, let me go back and redo them with this being the value of the base emitter voltage, and that corresponding collector current is 4.02 milliamps. If we go back to page 5, this was our expression for R pi. I'm going to use the value of V sub t at room temperature that Spice is using, and we had this value in Chapter 2. Beta F was 100, and our I sub c, I'm going to use the calculated value here of 4.02 milliamps. And I get 643.4 ohms, close to what we had before. And then on page 6, we calculated the voltage gain as being minus 66.7 K divided by R pi. But now R pi is equal to 643.4, and that gives me a gain of a minus 103.7, a little bit smaller in magnitude than we had before. My input impedance is 10K in parallel with 5K in parallel with R pi, and that's 539.3 ohms. For my first graph, I plotted the output over the input. The output, if you look at the previous page, is node 7, and my input, this is to the right of the 500 ohm resistor, is node voltage 2. Now when you say the ratio of these two, you're asking for the magnitude of the phasor. You could also do this in dB. I did it in regular units just to show you how the gain rolls off towards 0. Here's my gain. It increases with frequency, then levels out. What's happening here is those capacitors are blocking the signal as the frequency gets lower and lower. And you can see here we eventually level out at 103.539. We'd hand calculated the magnitude to be 103.7, so we're getting very close. This range of frequencies over here, we're calling the mid-band result, and it's actually where we drop 3 dB, or 0.707 times the value that's here. And we'll see later in Chapter 10 is that if you increase the frequency more, eventually this will come back down again. And that's due to some capacitances across the base emitter and the base collector. This is going to limit the overall bandwidth. But for right now, this does the audio band. That's all our model is really covering. I also want to look at the phase angle because the gain was negative. Plotted the phase angle of the numerator minus the phase angle of the denominator of this expression. And you can see here as the frequency goes up, it eventually approaches a phase angle of minus roughly 180 degrees. Give us, again, a negative gain. Next, plotted the input impedance of the circuit. And that's going to be the magnitude of the voltage to the current coming into the circuit. So node voltage 2 is where Vin is, and the current that's in the resistor, because I picked the nodes on page 8 to be between nodes 1 and 2, that's the current that's entering the capacitor. And again, these are magnitudes of the phasors. The default is an M here and an M here. And you can see as the frequency goes up, eventually we approach 539.767 ohms. And we'd hand calculated 539.3. As the frequency gets lower, we approach more and more of an open circuit. That's because of the capacitor C1. Looks like an open circuit for DC. And I also then plotted the angle, which would be the angle of the numerator minus the angle of the denominator. And you can see it kind of wiggles here, but eventually approaches 0 degrees. When those capacitors become a short circuit, We basically just pass the signal and we just have a resistive circuit. Let's take a look at the results in the time domain. Let's do it at 10 kilohertz because that's where the Bode plots are kind of leveling out, not changing. So I have the same file I had before, but I'm going to replace .ac now with a .transient. Well, normally we put 0 here to start showing the results, but there is a long transient analysis. I had to play with this and find where the voltages across the nodes in the circuit stop changing. That was after about 198 cycles. So I plotted another 2 cycles, and that's what we're going to take a look at in the following pages. If you take that difference of here, this is 0.2 milliseconds, and I divide that by 200, I get 1 microsecond per step. We did hand calculations based upon our value of 0.7 for the base emitter. I have to go back and change that if I'm going to compare the simulation to the hand calculation like we did on page 8. The base emitter voltage we found in terms of Zn, voltage divided with 500 ohms. That's now not 515 micro, but 518.9. And then peak to peak would be double that. The output voltage was the voltage gain, which is now a minus 103.7, times this base emitter voltage. And that gives me now minus 53.8 milli times the sine of omega t, or peak to peak of 107.62. And then we also found the collector emitter voltage with a DC value and an AC. The DC biasing in this simulation was 6.93, so it's a little bit different than what we hand calculated. And then here's our peak to peak of the sine at the output. I first plotted the voltage across the base emitter, which is between nodes 3 and 6 if you go back and take a look at the schematic on page 8. And you can see here that the average value is around 0.81. That's what the simulation found for the operating point. And you can see that there's an AC riding on top of that. The voltage here, peak to peak, is 1.038 milli, and we had calculated 1.0378 milli. Here's our DC level with an AC riding on top of it. Here's the output voltage. You can see it has an average value of 0. And then we can get the peak to peak here is 107.417 milli. And we'd hand calculated to be 107.62 milli. So again, very close. And then I plotted the voltage across the collector emitter. Just as in the previous case, you can see there's a phase inversion in my results from what I had as the input voltage. You can see the average here is 6.9283, which is again what the simulation had said the operating point was at. And the peak to peak here is the same as the previous case. It's 107.415. So again, you can see there's a DC level and an AC riding on top of it. You can see the phase shift here of 180 degrees. We block this so that we don't give a DC voltage to a speaker if that's where the output's eventually going to go. Now let's go back to page 8 again. And I did some sketches here that I thought might give you a better picture of things. Here's my input voltage, just some sine wave. And I took a look here at the output voltage. And you can see it's a phase inversion of the input. And then I took a look at the voltages across these 3 elements. The voltage across here, if you look in the simulation, I didn't plot it, it's just 4 volts. And the reason is that this capacitor looks like a short circuit for AC. But part of the biasing is that there was a current flowing in here and that caused a voltage around 4 volts. Then the collector emitter voltage is the same as the output voltage, but it's riding on about a 7 volt level. And it also has that phase shift. And if you look at the voltage across here, it has an average value of 4. It has the opposite phase of the collector emitter voltage. I didn't show all these in the simulation, but you can look at those if you like. But I want to show something here that if you take a look at the voltage across this resistor, the collector emitter, and the emitter back to ground, the voltage at any instant in time has to add up to 15. Here's on the average 4 volts, 7 volts, and 4 volts. I get 15 volts. If this starts to go up, this starts to go down so that the total stays the same. The sum of these two is always equal to 11 volts. Having these pictures, let me make one more observation or comment like I did back in chapter 2. We've been talking about a cue point in this chapter and some of the previous chapters. If this signal starts to shrink, then this starts to shrink and so does this, and likewise this. As the audio signal shrinks, we wind up at this biasing point of 4 volts and 7 volts, and we call that the cue point. I like to call it the quiet point, where the audio signal goes to 0. And this is a Pspice simulation of a common emitter amplifier.